Can you see the full screen?
Yes.
All right, cool. Thank you very much for the warm introduction, and it's a great honor for my part because, well, I had a wonderful guidance from Jimeng during my Georgia Tech years, and now being a professor and being invited here is like it's a whole new meaning to me. So it's a great honor to be here. The talk title is, as it says here, Interactive Evaluation of AI's Multimodal Medical Reasoning Capability. I put the interactive thing here specifically because I want to talk about that part as we move to the third section of today's talk. So I can skip all this because the introduction was already did me justice. So I have a total four, except for the summary. It's a three part talk. The first one I'll talk about why I think evaluating is important, especially these days with the LLMs. I focus a lot of my research on evaluation of LLMs or AIs or multimodal LLMs, all that kind of stuff. So I'll talk about the general idea of evaluation and then briefly introduce or touch upon these individual work that I did in my group. So you can think of this as like a story rather than a research talk. You can think about it as like a life story or like a research story. So these are in the chronological order. So I can talk about these individual work very briefly, and then move on to today's main topic, which is interactive evaluation. So now we live in the era of agents. So I think the evaluations, the paradigm has also need to adapt to the agent, the era of agents. So I'll talk about that. So beginning with the generic stuff. So I talk about this a lot whenever I go to like AI medical conferences or workshops. Why I think this is important, the evaluation. So suppose that anyone, any entity, any person comes to you and then they claim that I know medicine, so hire me as a doctor, or I know law, so hire me as a lawyer, attorney. You don't blindly just let them, you don't hire them blindly. You have to like evaluate whether their claim is true. So it's the same thing with the AI. If the entity is an AI, it could be anything though. It could be a dog, it could be a cat, it could be a frog, anything but in today's topic, let's keep it to AI. So if an AI says, I know how to predict whether a patient will die or not within the 24-hour window, then like how do you know that it actually learns something useful and it's grounding the claim to actual knowledge. So when it's like simple AI, like linear models, like logistic regression, you can directly study its coefficients, the parameters. So if, for example, if the feature for like smoking, like whether the patient smokes or not, if the value of that feature, the parameter value of the corresponding feature of the smoking is positive, then it kind of makes sense because the death, the 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 outcome being like the patient being dead in 24 hours, that outcome is positively correlated with the feature, the smoke, because it's the parameter value is positive. So that kind of makes sense. So we can see what it's learned and then whether it aligns with our domain knowledge. And same goes with like rather simpler models like confidence or RNNs, which are nonlinear models nonetheless, but still way smaller in size compared to modern LLMs. So researchers have developed a lot of like cool techniques such as GradCam or layer-wise relevance propagation or like perturbation methods or like studying attention patterns. So you can dive into like its internal thinking. Like you can at least indirectly, kind of understand what's going through its parameters. So, for example, if you're given an image and then the model says cat, and you use the GradCam to see where it's looking at, and it actually is looking at the cat, then you can kind of trust the model. The RNN or transformer, you can study attention and what, as I said. But what happens when it comes to humans? So when it comes to human, can we actually study the parameters of human, which is basically our brain? So can we like dissect the brain or do an MRI and then verify that his neural structure actually encodes legal knowledge or medical knowledge? Like we can't do it now, and we're not sure whenever we will actually be able to do it. So I think personally, we turn to these three methods of evaluation. The first being written exam. So you ask a question to the subject, to the entity, and the question that we know the answer of, and if he or she gets it right multiple times, statistically reliably multiple times, then we kind of believe that, oh, he or she knows what they're talking about. Even though we have no knowledge at all about how the brain works, we just believe them. The second one is kind of like an open question, open-ended question. You let the subject write a report or debate or do like a defense. So that's the number two. Number three is, I believe, has the strongest evaluation power. So which is to put the subject into an experiment in practice. So if a person comes along and says they know how to drive a car, then you actually let them sit in the driver's seat and then do a parallel parking, do an S course, T course, gas and brake, and all that. So you can actually see them in practice. So if you think about pharmaceutical companies, when they like manufacture a new like cancer treatment drugs, the best way to see its effect is to just give that drug to everybody. Like healthy person, cancer patients, anyone, like old, young, women, men. You just give the drug to everybody, and if the cancer patient survives and the healthy person is intact, then it's working. So that the practice or the controlled experiment has the strongest power for evaluation. But unfortunately, the third mode, the controlled experiment, takes the most time, most effort, most money. Sometimes it could sacrifice human lives. So it's not very scalable. So scalability wise, number one is probably the only way we can rely on. So all the like tests or like license exams or like uh, those the national exams, they're all like written exams. If you think about like college entrance exam or bar or medical license exams or civil service entrance exams, like anything you can think of, it's all mostly exams, because written exam is probably the only way, at least for now, that is scalable, meaning automatically evaluable. So we turn to number one. That being said, so what about LLMs? So LLMs are just big transformers. Everybody knows it's just like 100 layers of transformers. But still, in terms of pure parameter numbers, the size of parameters, it is way closer to humans. So modern LLMs like GPT-5 or like Llama 4 or like DeepSeek, those are like in the like 100 billions or maybe in the trillions. We don't really exactly know about the commercial LLMs, but still, like probably they're in the trillions. So compared to that, human brains or the connections between neurons, there are about like 100 trillion number of them. So, and if you think about linear models, you rarely use more than like 10,000 variables. So purely in terms of parameter size, LLM is already way closer to humans than to its distant ancestor, the linear models. And it'll probably only accelerate, because if you think about if we develop more easier way to generate electricity, or if there are more powerful GPUs coming in every single year, it'll probably go to like 10T, 100T, and so on and so forth. So if we can't do this with humans and we turn to this written exam, probably we should do, or practically speaking, we should do the same for the LLM. So I know there are researchers who are really, they strongly believe that they can understand LLM because we have all the parameters. We can poke at them, probe at them. So we can do a lot of stuff with fun stuff with LLMs. But I personally believe it'll be either impossible or take really, really a long time to understand how LLMs think. But at least we can do a test. So I'm an EHR guy, so I play around with a lot of different modalities of EHR, like tables, structured knowledge, images, EKG, time series data. I haven't done this, but hopefully someday I can handle the videos as well and unstructured text. So I'm interested in verifying whether LLMs or any AIs are actually they actually understand these different modalities of EHR like humans do, like experts, like physicians do, so that we can trust them when they like do like a decision support system, or when they predict some stuff, or when they prescribe medicine to the patient. We want to be able to rely on them. So that being said, I think it's already kind of being a standard in the general domain when, for example, when Google or Anthropic or OpenAI, they announce their new GPT-5 or like Gemini 2.5 or something, they usually say, "Oh, our model got a gold medal in International Math Olympiad," or "Our model got some rank, some score in the Codeforce code testing exam or competition." So it means that they are already relying on a impartial third party constructed exam, and that's the only way they can actually like show off how great their AI is. And I think it'll be the same in the special domain, not in general domain, but in special domain like legal or medicine, education, manufacturing, like all these different fields will be filled with exams. I mean, we already see that in the academia, but in reality, like actually, it might be like a necessary test. Like if your AI passes this test, then we'll put it in a controlled exam next year, like led by the government, something like that. So that is number one. And being able to solve the exam itself has value because you can make anything as an exam, like patient centric question answering, like what did I forget to take, or what's my medication. You can ask that question and then the AI can answer. Or operations, like can Dr. Kim see more patients today, or does he have 15 minutes? That can also be made into a question. And if AIs can solve it, it can probably help out in the operations side. So it inherently has its own value. All that's good. So it's good for so tests for the LLM in terms of EHR understanding. It's all good for like actually evaluating AI, and it has its own value. But I believe there are a lot of blockers that prevent us from actually having this like really, really, really adopted. So I think there are three major reasons. One is that in order to make an exam out of a clinical data, you need clinical data, but clinical data are private data, so it's really hard to get your hands on it unless you are affiliated with a hospital or you use open source data set like I do. Number two is if you were designing an exam for AI regarding their like I don't know like grade school mathematics, then anyone can design an exam because as long as you pass high school or you have like a college degree, you're fit to go. But when it comes to designing a test like medical test for AI, there are only so many people that can do it. Like only a handful number of people who are like who are qualified to do it. It's either the doctors or the nurses or the pharmacists or like the dentists. Only those people can design or make the question set. So there aren't enough people to, dive into this effort. And number three is a bit more engineering, because there are a lot of modalities here, as I said. If you start combining these different modalities, then it's like a power of like two to the power of something. So you need to have more questions, and then you need to test the AI for more longer to get to get a confident outcome. So that's the engineering side. So all this being said, I've been studying this. I've been doing this kind of question answering thing since 2022. So I'll start with that. So the very first thing I did is developing a benchmark data set for EHR, the structured data set, a structured database. I've been playing around with EHR, the database, a lot during my PhD and also after PhD. So this is kind of a natural course of action. So if, for example, you asked how many patients were admitted to our hospital last year due to COVID, and what were the male-female ratio of those admitted. That kind of question can be answered by EHR because you can just go through the database and then just calculate the number. Another question could be like, what are the survival rates? What is the survival rate of the patient who were diagnosed with this disease and were prescribed with that medication? That also can be calculated based on your database entry. So as long as you the agent or the AI can translate a human question into a SQL, which is a database language, then you're good to go. Then as long as the query language SQL is accurate, then you can retrieve the answer. So that's why we framed it as a text to SQL paradigm. So we did a poll in a local tertiary hospital. So we gave coffee coupons to a bunch of people like nurses, medical doctors, the professors, insurance reviewers, IT engineers, researchers, and the question was, if you had an AI speaker on your desk, what kind of question would you ask every day, like routinely, if you had some question about EHR? So that was our survey. So we got about 2,000 questions collected, and we manually reviewed all of them. And then we categorized them to different categories, like, oh, this is diagnosis-related question, this is medication-related question, this is like lab-related questions. So depending on the category, we templatized them like this, and then we built a SQL, corresponding gold ground truth SQL query for each of the templates. So we could make about 24,000 pairs of NLP or text to SQL pairs. So This was in 2022, so there was no ChatGPT around. So we actually used T5, which was kind of like the most powerful model from powerful like language model from Google. So we trained T5 on our training set and then tested on our test set. And you can see that the execution accuracy, which is when you run the SQL query that was generated by T5 and then run it, do you really get the answer? So that's the execution accuracy. And 86.6% is like kind of okay. I think it's okay in academic standards. Like we only have like so many, we only have like 4 GPUs, 8 GPUs, and we are only just one PhD student. So I think 86.6 is like kind of impressive. But if you think about deploying the system into a hospital, then this is like unacceptable because this kind of question answering system will be used to make like support the decision making process of like nurses or the doctors. And if the accuracy is only like 86%, then that means like you're missing 14 questions out of 100, which is basically saying you are going to kill 14 patients out of 100 patients, drastically speaking. So this is completely unacceptable. And I think an acceptable range is like 99.999 or something. Like if, as long as it misses one question out of 10,000 or maybe one question out of 100,000, then probably the director of the hospital will take us seriously. So there's a pretty big gap between what we can do in a single lab in academia and what the hospital is expecting. So it's a gap that needs to be filled, probably not by a single lab, but probably like by the whole academia, or maybe the industry for that matter. So this was our very first work. And we expanded this in the next year by adding one more modality on top of it. So it's now database plus images. So you can see the black box here. The kind of questions that we want the AI to answer is like, has this patient, some patient, received some procedure, like cardiac catheterization procedure? And also, was there some abnormality in the cardiac silhouette of his or her X-ray? So in order to answer this question, you need to look at the database to look about that procedure thing, and also look at the X-ray to see where there was anything wrong with the cardiac silhouette. So, and then you need to do an intersection of the information gathered from the two, and then do a bit of a reasoning, and then answer the question. So, I'll skip the detail of how we actually constructed the question answering data set. The beauty of benchmarking is actually building a rigorous set of question answer pairs, so that there is a high correlation between the outcome of the test and the actual, like practical performance. But that's just too much detail. So I'll just skip to the solution part. So we have a multimodal question. So no longer can it be solved by a single text-to-SQL model. So now we are in 2023. So there's ChatGPT around. So we feed the question to ChatGPT and then ask whether this question can be answered either by only looking at database or X-ray or both at the same time. And if it's both at the same time, then the ChatGPT will write a SQL query with a very, very, very basic tool calling functionality. So this was like all before like agent era. So we didn't think of the paradigm as like tool calling, but it's the same as tool calling. So there's another function or some API that is able to understand X-ray and then get some information out of it, or in a linguistic textual form. So that information will be plugged into this SQL, and then you run this all together, and then run it through some parsing engine, and then you get the answer out. So that's a very basic tool calling agent. And you can see that the accuracy of the table related, basically text to SQL performance has now risen to 93. So compared to 86, 93 is a big jump. And unfortunately, this was not our doing. We didn't do anything. We just used ChatGPT, and we got 93. So compared to 86 and 93, like you can feel the power of enterprise or capital. So this was not our doing. So it's a bit of a bitter lesson. If we poured a lot of effort into increasing this to like 87 or 88, we might be able to do it, in 6 months or two, in 6 months or so. But just waiting around was a bit of a wiser choice. And if you look at the image side, execution accuracy is 48%. So this is like way better than random, because we designed the question answering data set to have a score of 5% or 10% if you just do if you do a random choice. So 48 is definitely way above a random choice, but still it's not 99%. So there's still a big gap. And personally, I think the reason that this is hanging around in 48% is because the tool, the X-ray interpretation tool or the classification tool, we made it, but when we were training the model, we used about 200,000 X-ray images. And if you think about all the different diversities of all the different things that can be captured by X-ray, 200,000 images is just not enough to build a foundation model. Like you probably need like at least like 50 million or maybe 100 million images to build a X-ray foundation model, which I can't do as a KAIST professor. You have to be like a very prominent person in a tertiary hospital probably. So um, we stopped we stopped developing foundation models for X-ray for that reason. At the same time, 2023, we happened to be the group that made question answering data set for ECG for the first time. So we were interested in ECG for quite a long time, but it was mostly for like detecting anomalies or arrhythmia or some cardiac disease. But we've never seen a formal benchmark for AIs to take to estimate their ECG understanding capability. So we just did it. And the question is like this. So you have a 12 lead 10-second ECG, one or two, and then you can ask a bunch of questions like the findings, diseases, diagnosis, or some numeric values like what are the RL intervals, what's the height of the QRS complex, all the different kinds of questions. So this was adopted by the Google team to evaluate the Gemini and Gemini's multimodal reasoning capability. So if you build a like nice benchmark, somebody will pick it up. We did all again here. We did a very like basic form of tool calling. So instead of actually developing a multimodal LLM or maybe multimodal BERT for that matter that can understand ECG natively, we actually just developed a classifier that can just translate this ECG signal into linguistic signal like here. Like, oh, there's like certain chance of this, certain chance of that, certain chance of this. So this is basically a multinomial distribution over different findings and diagnoses. And then you pass this to the LLM, then the LLM can just do a lot of different stuff. The LLM can paraphrase it, summarize it, do a question answering, have a conversation about it. So you don't have to actually train an LLM to understand ECG using fine tuning or like multimodal fine tuning like LABA. As long as you can capture the clinical information residing in this raw signal and then convert it reliably into a text and pass it to the LLM, it might work. So the comparison between the two paradigms, which is here, M3A is kind of like a BERT-based multimodal model. We trained this one with about 250,000 multimodal samples of ECG in question. Compared to that, this is the very simple stuff with a classifier hooked up with the GPT-4, and if you see the performance gap, this 71, 76, 48, 58, this is a rather big gap, 38, 35, 40. So you can see, even though GPT-4 has never ever seen an actual ECG, it might have heard about ECG, reading all the medical textbook and whatnot, but still, it has never seen ECG, as opposed to this guy. This guy's seen like 250,000 samples of ECG. But the gap is not as wide as you might think. So this could be like a viable solution for like not big labs, like Google or OpenAI. They might be able to build an LLM that can understand PET scans, MRIs, X-rays, ECGs, echocardiogram, all the different modalities in just one single giant model. They might be able to build it because they have like trillions of dollars. But small time labs like or hospital, they don't have the money, they don't have the engineering capacity for it. So actually, just developing a single converter that can convert raw signals into a reliable textual information and just pass that to the LLM, that might be a feasible solution. And it's probably easier to maintain and develop and advance in software engineering wise. So that could be a good solution. The next one is the one that we did last year. So I've put off handling text for some time because text has too much big of a degree of freedom, meaning that when it comes to ECG, for example, ECG it has a very specific purpose. Is to record the electrodynamic like movement of your like heart, and that's it. So you never ask questions based on ECG, such as like, oh, does he have a broken bone in his foot, or does he have something wrong with the brain? We never ask that question on the ECG, but text. It can say anything. It could say it about the patient's status. It could say something about the patient's social relationship with his family, his or her family. Anything can go. So it's really hard to design a benchmark for the AI to see that whether the AI understands clinical text because you can ask anything. So I put off doing this for some time, but luckily I had the chance to collaborate with Naver. So Naver is like a kind of like a Google of Korea. It's a big giant tech in Korea. So they have a healthcare team, and in the healthcare team there are a couple of doctors. So they volunteer to help us out. So what we did is we only focused on discharge summary from Mimic, and we intentionally constructed a very challenging question answering data set. So for example, you have to read these two discharge summaries, which are like about 3,000 words each, and then read the question, and then select the right option. But the options are really confusing. Like there's only like 1 or 2 word differences between the two. So you have to completely understand everything to get the question right. So you can't really like random chance your way to like 80% or 90%. So that was the whole like intention of this benchmark. So what we did is we had like a seed questions from GPT-4. So we feed these discharge summaries to GPT-4 and then ask what kind of questions would be interesting clinically. So those questions we've generated about 1,000 questions, and every single questions were vetted manually by 3 clinicians over 6 months. So it's like a arduous labor. So I don't think we can ever do it again, because it was such a torture for the clinicians. So they had to actually read every single question, see if the question was like clinically relevant. If not, they had to modify it and read the answer choice, correct answer choice. If the correct answer choice was not correct enough, they had to modify it. And also read the incorrect answer choices. If they were too easy or too irrelevant, they also had to modify it. So that went on for 6 months. So you can see the amount of labor that went into this benchmark data set. So once we built it, we actually tested the popular models of that day. So this was like 2024 June-ish, I think. So GPT-4, like the big models to all the small models. And there are a lot of numbers. Like we did multi-choice question format, also open-ended format, like easy questions, hard questions, a lot of numbers. But all in all, 4 lessons we earned 4 lessons. And this, the order is based on the importance or the impact of each feature based and how it impacts the outcome on this particular data set, this benchmark. So the most important thing is model size. So if you look at Llama 2, 7B, 13B, and 70B, you see a like linear increase. So it's 65, 73, and 84, which means that as long as you get bigger, you get better. But if you imagine what Meta was doing, probably when they were building like 70B, 13B, 70B, I don't think they would have intentionally put more medical related text into 70B as opposed to compared to 7B. They just put more data, and then it just performs better. Same goes with foundation models. Foundation model meaning like if you compare Llama 2 and 3, there's 10 points gap between the two, which is very significant. But again, if you imagine what Meta was doing, I don't think they intentionally put more medical text into the 3 version compared to the second version. So these two, what we usually play around, the researchers of a single lab, like we do like instruction tuning, SFT, alignment tuning, or GRPO, whichever. Like we play around with that a lot, but none of those really don't matter in front of these two. Like model size and foundation model way more outweighs the importance of or impact wise these two. So, for example, if I saw that Llama 2 came out and then I decided to, I'm gonna fine tune this, like I fine tune the hell out of this, and then get like 87, 88, and 3 months later, 3 comes along in 94. So, which is just all a moot point. So, it's really a hard time. It's a difficult time to be like an independent researcher when it comes to like large scale LLMs. If what you're after is performance, it's probably better to just wait around. So that was one of the bitter lessons that we learned. The last one of the previous paradigm, 2024, is the multimodal benchmark between text and database. So I've touched like database, images, ECG, text. So the long time coming, I really wanted to do a multimodal benchmark with text and database at the same time. But before doing that, we did a preliminary analysis, and then we figured out, we discovered that there are a lot of inconsistencies between the two. So, for example, this is a human written note, and this is like machine generated, or maybe people entered some stuff, but the database. And sometimes the dates don't match or the hours don't match. For example, like people might forget this summertime, but machines never forget. So there's 1 hour difference between the two. People might write for medication like a product name like Tylenol, but in the database it says acetaminophen. So there's another inconsistency like that. Or people might say like 10 milligrams or something, but because of the floating point operation, it might say in the database like 9.99999 milligrams or something. So they're all because there a lot of due to unimaginable diverse sources, there are just a lot of inconsistencies between the two. So we decided it's probably better to just focus on that first rather than building a benchmark. So and also these inconsistencies eventually trickle down to downstream applications like myself. Like I'm a data scientist, so I look at when I look at data like this, I consider them as ground truth. But ground truth is riddled with inconsistencies, so it'll trickle down. The quality of the outcome of the downstream applications will also go down. So we decided to come up with like a simple system. They can hopefully detect these inconsistencies on its own. So after some preliminary like data analysis and annotation, we found that most of the inconsistencies come from the charts or the labs because they have a lot of entries in the discharge summaries or nursing notes, and they have a lot of numbers. So numbers can be mismatched between the text and the database. So it's mostly like 70%, 75, like 3/4 of the error sources are chart events and lab events. The way we designed the system to automatically detect the inconsistency is very much similar to how the students annotated these inconsistencies, how they labeled them. So we feed the entire note to the LLM, and then the LLM just breaks down the notes into different sections because of the context window size, and then it recognizes potential entities, named entities that might be worth looking into. And then when for example, when it chooses SBP, then it needs to decide which table among the database it needs to look into. Like it could be stored in chart events, or it could be stored in lab events, it could be stored in somewhere else. So you need to decide. And when it decides, then it looks at the corresponding table, and then look at the schema, and then writes a SQL query. And then you have to expand the named entity into similar ones, like SBP could be systolic BP, blood pressure. Who knows what kind of surface form it is stored in the database. So you have to use like a dictionary to expand the terms. So once you have these, you run the query to the database, and if there is a match, then you can think of this as a consistent case. If there's zero match, then you can think of this as an inconsistent case. So that's the whole setup. And when you ran the system using GPT 3.5, which is, there are 4 models, but GPT 3.5 was the most powerful. And when you run it, the recall and precision is not very impressive. So the reason being, GPT 3.5 turns out to be not a very good named entity recognizer. So when it reads the notes and figures out, oh, I need to check this entity, check that entity, it can't do a very good job. So if NER fails, then all the downstream fails. So you can see why it has such a unimpressive score. But if we feed the ground truth entities, then it gets 86. And if you do some fine tuning or prompt engineering and whatnot, then I'm pretty sure you can get it up to 90, above 90, which then kind of leans into being useful in the real world. But the named entity is a big problem, and we are trying to solve it, but we still haven't solved it. Even with GPT-4 or Gemini 2.5, named entity recognition is really, really hard because medical text is riddled with abbreviations and different styles of writing according to different doctors. It's just it's a landmine. So that was a lesson learned. So this was all before 2025. So it was just a brief a summary of what we did so far with different modalities. But if you think about it, all the benchmark tests that I introduced right now, like the tables, the database and images, or ECGs, text, well, the last one, the multimodal thing, is not much of a benchmark. It's not a test, right? It's some application, but it's not a test. But except that everything was a single turn question answering. So you have a data set which consists of maybe 100 questions, and these questions are not related to each other. They're independent questions, just different knowledge parts from ECGs or notes or X-rays. So, and you solve them, and then if you get 80 out of 100, then you get 80% point. So that was the setup. But now we live in the era of agents, and agents can do tasks end to end. Like they can go to the website to figure out some stuff. They can look at the X-rays. They can look at the images. They can look at the database. They can interact with the person, like the doctors or the nurses, and then get a confirmation from them. So they can do a lot of different stuff on its own, and then finish a task from end to end, right? So I think correspondingly, the evaluation paradigm has also need to evolve into a multi-turn paradigm. So I want to talk about two things. The number one being chaining the questions together. So which means that, oh, I solve question one. If you get it right, go to question two. If you don't get it right, go to question three. If you get it right on question two, go to four. If you don't get it right, go to question five. Something like that. So I'll give you an example in terms of on X-ray, chest X-ray. So a lot of researchers, when they develop or train or evaluate a X-ray LLMs or multimodal vision LLMs, they usually rely on these two sources, the X-ray and its paired radiology reports. And when they build a evaluation that benchmark, or maybe fine-tuning examples, they do a pre-processing of the reports to get extract the question answer pairs. Like, is there opacity in the image? There is some mention in the opacity in the radiology report, so you can pre-process it and then get a question answer like, is there opacity in the image? And yes or no. Or what are all the diagnoses in the image? Oh, there's pneumothorax, pneumonia, yada, 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 atelectasis, yada. So you can do this, and then in terms of like, if you think about benchmarking, you can build a benchmark out of this and do an automatic evaluation and then say, oh, my AI or that AI got 90% in this X-ray benchmark. So that's what we do. But if you think about what goes on between when radiologists look at the image and when they write the report, there's a whole like cognitive process going inside their brain. So when they see the visual signals of X-ray, and then that fires up a lot of like vision neurons, and then it's combined with what they learned in the medical school, what kind of the experience that they gain from like all the years of looking at X-rays. It's all combined, and it runs a reasoning process, and then after that they write the conclusion to the report, like, oh, we should think about pneumonia, or this should be like tested, or this is probably this, or this is most likely that. Like, those are the conclusions. So, and also there can be human errors, but this is mine, because this is kind of mine. So modern AI being trained or evaluated with these two are actually missing all this cognitive process that radiologists are going through. And I think this is what actually the LLMs need to learn, the reasoning process. Not the source and the outcome. It's the intermediate step that really matters. So with this current paradigm, I don't think we can rigorously evaluate AI's reasoning because we're missing this part. And also, we can't do it. It's all based on report-induced QAs, which is full of just conclusions. So one of my students, Hyungyung, actually is scheduled to present this work in Europe this year, which is two things. So what are we going to do about the report-induced QAs? Like, what are we going to still, like, are we going to keep relying on the conclusion-based report-induced QAs? And the question is no, of course no. We want to extract clinical information directly from the original image. We don't want to rely on here. We want to rely on here. So that's number one. And how to actually evaluate AI's reasoning, not just, oh, is there pneumothorax? Yes or no. Is there pneumonia? Yes or no. Not that. So we need to ask a series of related questions, which is the chaining of Q that I mentioned before. So all we did is we can use any off-the-shelf segmentation model because X-ray is such a abundant in open source. There are a lot of abundant or open source images of X-ray. So there is already a pretty good performing segmentation models you can use off the shelf. So you run it on all the X-rays, and you can get the segmentation maps out of it. So all the bones, all the organs like the heart, the diaphragms, lungs, clavicles, carina, trachea, whatever. So you can get all these maps or the masks of individual organs or body parts. And then with these, you can start calculating pixel level like measurements or ratios. So one example is this. How do we decide whether a person or a subject or a patient, like held their breath for a long time with enough air in the lung? So because that's what you need to do when you're taking X-ray, right? So when I asked this question to a radiologist, they didn't know how to answer it because they intuitively know, because they've seen so many X-rays. They just know when the patient was holding their breath well or not. But that's not what we want. Intuition is not what we're after. It's the reasoning that we're after. So I asked him, like, I really bothered him, like, you must have learned this in the medical textbook, like how to measure whether a patient held their breath well or not. So they thought about it and then they just Googled it and they just gave the physician gave me this order here. So the way you do it is you need to first draw this line, this mid-clavicle line in your lung, and then there's a diaphragm, and then when the diaphragm and your, I think it was 10th or 12th, like some like maybe 10th rib and your diaphragm crosses each other, then that's a sign of good inhalation. If it's like 8th rib or 7th rib, that's a bad inhalation. So that's the reasoning process. So you can calculate this based on these maps because you have the diaphragm, you have the ribs with number 1, 2, 3, 4, 5, all the way to like 11 or 12. So you can actually calculate this with pixel level information. Another example is cardiomegaly. So cardiomegaly, they, like, physicians know how to tell a cardiomegaly, but the reasoning is what we're after. So I bothered them, and they came up with this textbook reasoning process, which is you first calculate the width between these two, the lungs, left and the right lung. You calculate the width of the left and the right ends of your heart, and then you do a ratio. And if it's above 0.55, then that's cardiomegaly. But if the view is not PA but AP, then it has to be 0.5. Like there's all kinds of if analysis in the chain of reasonings. So you can encode them rule based. Like it's not like you're not teaching AIs to actually run it or learn this using GRP or SFT. It's just rule based thing that is de facto standard because it's coming from the medical textbook. So we did this for 12 different findings, like inspiration level, cardiomegaly, trachea deviation. There's like 9 more, but I won't talk about it. So based on these knowledge, what we can do is we can build a question answering benchmark that is interactive. Interactive meaning, I'm not sure if you have ever read this kind of book, which is like a build your own adventure book. So you read this page and then, like, as a protagonist, you have to decide what to do. Like if you want to save your girlfriend, go to page 18. If you want to like, sacrifice your girlfriend, go to page 27, so on and so forth. So there's like a branching story arc structure in these kinds of books. And you can imagine like there's only one good ending. You start from here, the AI starts from here, and it can take a lot of different routes, but there's only one good ending. One good ending is the one that follows all the medical reasoning that we just established. So this is the benchmark. So the AI is given an X-ray, and then you ask the AI, can you see if the patient did like inhalation, like a good inhalation or not? And if the answer is C, I don't know, then we actually teach the AI to be able to do it. And if the answer is yes, like, oh, I think the inspiration level was good or bad, then we test its claim through the reasoning process. Oh, you think that? Oh, then how did you know? So you have to choose the right criteria. Like, oh, I looked at the diaphragm and the rib number, and then I did it. Then if the AI chose the right answer, then we go to stage 2, which is, oh, you think you know diaphragm and rib numbers. Then among all these images with different segmentation, pick the 12th rib and the diaphragm because you said you know it. And then if they did it, then we ask number 3 and number 4 and so on and so forth. So there's the good ending is when the AI got the question right in all the steps, all the stages. So that's the whole the setup of the interactive evaluation. So when he puts a lot of VLMs, vision language models, through this the benchmark, Gemini 2.5 Pro was the strongest. The completion rate being 17%. So completion rate is, I said there's only good ending, which is getting the correct answers throughout all the stages to stage 4, and we have like, I think we have like 1,000 questions or 2,000 questions. So this is a ratio of completion. Like so Gemini 2.5 Pro was able to get 17% of completion rate, and this is the best we can do. Open source models not doing a very good job. Depth 2 is when you test the visual recognition capacity of the model, and you can see none of the models on average passes stage 2. So when we ask, oh, you think you know some stuff, you think you know trachea, you think you know clavicle, pick that among the images, but it never succeeds. So you can see that, you can imagine all the all the multimodal language models these days, when you upload an X-ray and then you talk about it, it seems to get something right? But it's grounded on something completely different. It's never grounded on medically established knowledge, because this is medically established knowledge. This is like ground truth, but it never really gets it. So you can see the kind of a disappointing status of the multimodal language models in terms of X. This is only X-ray, so it might be doing a good job in CT. I really doubt it, but who knows? But X-ray, as long as X-ray goes, none of the models are really good at structural reasoning of their claims. Their claim being like diagnosis or findings. This one, yeah, we can. I think we can skip this. I have one more thing to go. I think it's already 50, so I'll just skip through. I'll like skim through it. So the second one is LLMs can simulate as users. So what I mean by is I'll show you some example. So LLMs, AIs or agents can interact with the world, with the tools, with the data, and also the people. And it's the people that I'm interested in. So for example, if I were to build a differential diagnosis machine, an LLM, then I want to test it. I want to test my LLM, my diagnosis bot, to see how well it does. So I usually, what I do is I like, I invite or hire some patients or maybe actors who can act as patients to interact with my bot, my product, and then I get a like accuracy or some performance metric out of it. So say it's like 80%, version 1. But then I probably develop version 2, maybe some prompt engineering, maybe some new architecture, new training set, whatever. I need to invite or hire the same group of people to get an accurate evaluation, and so on and so forth. Every single time, even like one tweak of, like prompt, I need to do this all over again, which is just not feasible, which is just not scalable at all. So my hypothesis is that if you can replace these people with LLMs, so if LLMs can role play as virtual patients, then these development cycles can be done purely purely with LLMs. So the development cycle can be way faster than actually inviting or hiring people. So this can be LLM, the doctor. The patient can also be LLM. So that was the thought behind the next project, which is patient simulator. So this will also be presented in Europe this year. So we set out to simulate ED patients, because ED patients there are a lot of different patients, like anxious patients, impatient patients, or someone who's like really worried about their health, someone who doesn't have their cognitive function really working well. And like there are a lot of different patients, and either nurses or doctors have a very hard time interacting with them and then see what's wrong with them and triaging them. So it would be better if AIs can do it. But then if we want to develop that AI, we need to be able to evaluate it, and that's where patient simulator comes in. So for example, if you have a certain profile with certain personality, certain linguistic capacity, and certain like memory function, then hopefully it can interact with the doctor or LLM doctor in that according to the persona. So you can see like if it's distrustful persona, it's constantly questioning, why are you asking me that? Why are you asking me that? Or why did you know that before? Like that was our hypothesis. That was our goal. So we used 5 different axes to comprise a person's persona, which is medical profile. So medical profile comes from Mimic 4. So we have Mimic 4, Mimic ED. We can extract a lot of relevant information from the discharge summaries, like age, the job positions, or the gender, family history, symptoms, yada yada yada. So that's the medical profile. Personality and language proficiency and medical history at recall level and cognitive confusion level. These were designed in collaboration with actual ED, like emergency specialist medical professor from one of the Samsung Medical Center. So she actually advised us to figure out what kind of personality she actually encounters in actual ED, and what kind of linguistic proficiency is appropriate for like elementary school students to like middle school students, or like like high school students and whatnot. So those are the axes that we defined. So after we did this, we wanted to evaluate whether the virtual patient that we implemented is acting just like real patients that the physicians see in the emergency department. So we built this kind of tool where there's like the persona. We don't give them the diagnosis, the actual diagnosis, but we have the personas here, the personality, language proficiency, yada yada yada, and then we let actual physicians that we hired from the internet. I think they're from the Philippines, so they can speak good English. So they interact with the patients like 5 to 10 minutes, and then they figure out what kind of disease they have. And also, while doing so, they were asked if they were following the personality that they see here, and the language capacity, and the recall level, and the confusion level. Also, the overall realism. Like, are these virtual patients realistic enough so that they act like or they behave like the actual patients that they encountered in the actual ED. So that was the question. And also the final question is, do you think this will be useful for like educational material in medical school? Because I heard from medical professors that medical students, when they want to practice their diagnosis or interaction training, they actually hire the actors to act like patients. So instead of doing that, maybe we can use the virtual patients to do that. So the answers were all kind of favorable. So like the 4 being the perfect score, high in the 3s. So that was our finding. I want to, if the time allows, I want to show you the demo for a very brief moment. Would that be okay?
Yeah, please.
Okay. All right. So, oh, there were some chat questions. I can answer them after this demo. So this is the demo that we set up. There are 3 personas or profiles that we prepared. These are fake actually because the real ones I don't think we were allowed to upload on the internet. So we made fake profiles as closely as possible that resembles like actual clinic profile. So I'm choosing 64 male with myocardial infarction. And the CFR is the linguistic capability. So A is like very beginner. And the personality is plain, just neutral. Recall level low. So he doesn't remember a lot of stuff that happened in the past, like what kind of medications he's taking, what kind of past diagnosis he had. He doesn't understand. The days level is like when you're traumatized by like accidents, car accidents, they usually don't have the cognitive function going so well. So but here it's normal, so we don't need to worry about that. So I already actually typed in, so I'm asking, hello, what seems to be the problem today? And then it says, chest pain, bad pain, go to arm. Because the linguistic capability is A level, so it's kind of like elementary school level. So if I ask, for example, I see, does your family have any hereditary diseases running? Oh, do you have any is running in your family? I'm hoping that what happened? Okay, I can start again. Okay. Oh, and the model that runs the patient is Gemini 2.5 Flash, I think. So I'm asking, I see, do you have any hereditary disease running in your family? And I'm hoping because of the word hereditary, which is kind of like advanced word, like it says, what? I don't understand. So you keep interacting with that, and then it'll probably say, whenever I use like medical terms, it'll say, I don't understand, like, or don't know, or something like that. So in that case, it's really hard for the physicians, the Filipino physicians, to actually get the correct diagnosis. I'll just do one more. So the linguistic language ability is C with over anxious, so worried about his or her health a lot, and high recall normal. And I'll see, hello, what seems to be the problem today? And yeah, it's saying a lot of words. First of all, he's very good at English, so you can see like a lot of advanced vocabulary, and super worried. Like I'm profoundly worried it's something catastrophic, quite nauseous. It's vicious sensation. It's just like because he's an over anxious person, so he's worried about his health. So I kind of say, please calm down. Would you tell me when symptom begin? And yeah, he's not happy that I said calm down, doctor. Like, the like terrifying ordeal. Like, it's like a lot of like exaggerating words. I immediately fear the worst. Like truly, Mario. Oh, he kind of like suspects true myocardial infarction. That's funny. Or something even worse, like something even more insidious. Like, sometimes when I do this demo, I hear like this might be cancer, or is it terminal, something like that. So it's very funny because um, I was surprised that LLMs, by the LLM's capability to act as real patients, because I'm not sure where they picked it up. When they were, I'm assuming when they were reading the internet text and whatnot, they probably picked up the uh, the, the transcripts from maybe like medical dramas like House MD or something like Good Doctors or ER. Like then they can probably see how patients behave. I think maybe that's where they picked up. But they're really doing a really good job because the medical professor from Samsung Medical Center, she was literally angry with this virtual patient because it reminded her of the actual patient she met yesterday. Like, oh, when are you gonna give me a cup of water? Like, do I have to take this test, or like I really want to go home? Like those like typical responses really were really being acted out by the LLM. So that was like quite interesting, like how well they can perform as an actor. Yeah, this is the end of the demo, and now this is a paper info. If you're interested, you could check it out. Right. Summary, yeah, the LLMs can be. My personal opinion, but I don't think it's really easy to really figure out what they're doing underneath the hood. But at least we can check the input and output and evaluate it. So in the era of agent, it's a bit more challenging, but we can still do it. So we can still evaluate based on the interactive setting, or maybe using them as a end user, not just patients, but any service users. They can simulate if we do things right. So I think there's a lot of places to explore in terms of agent evaluation. Right. Yeah. Thanks for listening. And if you have any questions, I'd be glad to answer. Thanks.
Great. Thanks, Edward. There are a couple of questions in the chat. I don't know if you want to answer.
I can. Yeah, I'll read them out. Question from Weibing: Where and how do you get those questions for EHR Node QA? Oh, so the questions were first generated by the GPT. So we feed the discharge summary to a HIPAA compliant GPT, of course, and then we ask the GPT, like, can you think of some clinically relevant question answer sets? And they generate a bunch of them, like thousands of them. But that's after that, that is where the actual doctors come in and they manually vet all the questions for 6 months. So we can really say that this is a guaranteed question answer data set. I'll move on to Junhao. How can information across different modalities, across multiple visits, be effectively and accurately unified into an LM understandable, learnable way? Or what do you think is the key factor influencing this information on patient conditions, fusion state? I'm not sure when this question was asked. Was it around like patient simulator? Oh no, it's not.
I
It's
think it's
1235.
about that. It's about how you include the SXR, ECG, EEG, such as the signals, or
Uh-huh.
like when you're considering all of those information, some of them are time series and some of them are different with a node format, the textual format.
Right.
I
Uh-huh.
understand most of like the studies will convert it to the textual information, but I'm
Uh-huh.
thinking about whether it will be resulting a loss of the information and how you think about the combination of the time series, non-time series, and also the textual, non-textual informations.
So when you say time series, I'm assuming that you were referring to the ECG, but ECG is taken over only 10 seconds, so I don't think it pertains to like multiple visits. But that actually is a concern. Like if you want to collect information from multiple visits, then the ones that happen in between are all lost. If you only rely on EHR, so there's only so much you can do when you want to like learn the representation of the patient status. I'm not sure if that's what you're alluding to.
Yeah, so for time series, I'm more referred to the multiple visits because you also
Uh-huh.
have the discharge summary one, discharge summary
Uh-huh.
two.
Uh-huh.
So the
Uh-huh.
person could be discharged multiple times. Is there any
Right.
relational thing can be learned by the large language model when doing the question answering? For
Mm-hmm.
example, refer to the last visit and the next visit, your condition is better, or there's a factor in the last visit caused some problem in current visit.
Mm-hmm. Yeah, I mean, for example, this benchmark here is not set up to test the kind of capability, like whether LLMs can take into account all the past visits and then have that in the context, and then maybe like diagnose or consult the patient or consult the doctors. It's certainly a very challenging thing to do for the patient for the LLMs, but it's also challenging to actually set up an evaluation strategy, because if you want to see if LLM can do that, take all the history into context and then do some question answering or reasoning. If you want to evaluate that, then you need to make up those questions. But if you have this long history, then making those questions becomes a very complex task. So there is always the same thing. Is if you expect great things from LLMs or AIs, you need to be great to begin with, so that you can create a testing set or benchmark. So there's always this kind of a paradox, if you know what I mean.
Thank you.
Question from Junhyang. You introduced a study where the LM assessed X-ray images to determine whether the patient maintained proper inhalation. When the model responded, I don't know, you mentioned that it then provided multi-step guidance. Could you explain how this? Oh yeah, sure. For example, was the guidance added to the prompt in as? Yeah. So the short answer is yes. The guidance was added to the prompt. So right here, if you select I don't know here, then the AI goes to the path 2, which is this is how you first of all, I need to see whether the AI actually at least knows what a diaphragm is, at least knows what a rib is. So I first test that, like among these images, can you figure out which is a rib or which is diaphragm, which is a different question here, because this question doesn't tell you which organ to find, because you have to find that organ. But in here, in stage 1, we kind of check, oh, you need to find ribs, you need to find diaphragms, and you need to combine them together to calculate which rib is crossing the diaphragm, and then if it's the second rib or the third rib or whatever, then that's a good inhalation. So we do it stage 1, 2, 3. So once we do this, we put all those things into the context window, and then goes to the stage 1, to the path 1, or path 1 here. But when we do it, we switch the images. So the image used here and image used here is different image, obviously. So then it's hopefully when it answers all the question right here, then it's ready to solve the question here. So I actually skipped it, but when you do that, the completion rate increases from 17 to 55. So it's kind of like working okay. Like Gemini 2, at least for Gemini 2.5, it can use the knowledge. It's basically a one-shot knowledge. So it's your one-shot fine-tuning or one-shot prompting the AIs to, solve the question. But it's hopeful. But it's not. Interestingly, it's not 99. So if it was taught to like a medical student, immediately they would just figure out how to generalize the knowledge and then solve the question. But interestingly, Gemini 2.5 cannot. But the good thing is, at least the depth has increased to 2.62. So at least from time to time, it can crush the stage 2. So that was what we learned. Hopefully that answers your question. Question from Lynn. If AIs are mainly acting as simulated patients, they seem to be more useful for training doctors than for diagnosing. Sure, yeah, diagnosing, yeah, obviously. So it was the purpose was twofold. It's either used as educational material for training doctors, or used as evaluation tool for evaluating AI bots, AI doctors. So it's twofold. In real clinical practice, how do you see the balance between AI assisting doctors and doctors remaining responsible for patient care and final decisions? This is a very hard question. I think, personally, a lot of doctors are already using AI, unofficially or officially. At least Korean doctors are doing it. When they're like treating patients, there are two screens. On the one screen, it's about patient record. Second screen is LLM, like GPT or Gemini, and they're looking at the both thing and then talking to the patient and then diagnosing. So I think they're already doing it. How to make it official is, I don't think I'm the right person to answer the question. Probably a lot of legal stuff involved. Like if the doctor made a wrong decision because ChatGPT said something stupid, then whose fault is it? I think for now, it's doctor's fault because he chose to use GPT and then he chose to believe what it said and then made a final decision. So the responsibility falls on to the doctor, but I don't know what will happen. I'm not really sure what will happen in the future. Yeah.
Sorry, can I ask a question online?
Hey, you go.
Yeah.
You're great. You can ask.
Yeah.
Go ahead, please.
Yeah. So for your patient simulator work, right? So one side is configure the patient communication style and emotions. Another side is make sure patient stick to a script, which is more closer to the clinical reality.
Right.
Like I maybe didn't capture all you said, but how do you think about that like how we ground the patient simulator in the clinical scenarios?
I actually didn't put that in the slide because it's just too much evaluation. We did like whole a lot of evaluation. Just like you said, we wanted to see if the patient simulator was sticking to its medical profile, not going off rails. So that was one of the evaluation. Another evaluation was a set of like, does it stick to the personality? Does it stick to the language proficiency? That's another stuff. The third one is if the simulator, like if the LLM makes stuff up that is not in the profile, is it always wrong? Because maybe the profile says pneumonia patient, and that's it. And when the patient LLM talks with the doctor, and doctor asks like, "What are your symptoms?" and the patient says, "Oh, I have fever," then that's not really hallucinating because it said you are a pneumonia patient, and pneumonia patients often get fever. So when it says fever, that's not hallucination. So that was the hardest challenge to evaluate. So we spent a lot of time and money because we hired like 4 Filipino doctors using like thousands of dollars. So we did a pretty like rigorous job. But it's 4 doctors, so it's not statistically like super rigorous, but still it's better than nothing. So yeah.
Yeah. So one idea, what I'm thinking here is, should we use more this kind of disease symptom knowledge graph thing to be grounding the, large language model mainly in this kind of plausible reasoning space? Or from your experience, like don't use knowledge graph, just ask a model to do plausible, inference is sufficient. Like, what's your
No,
experience?
I think it definitely helps if we have the knowledge graph embedded. Like, for example, pneumonia will have a lot of different relations, like symptom relation or like is a relation or child relation. And using that, AIs can stick to it can only say stuff that is more aligned to like established medical knowledge. It's just that, but this needs to happen in real time. Like chatting needs to happen in real time. But if you let the AI just explore KG while making the answers, then it may take some time, like a few seconds or a few minutes. So that's not what we want. So I think we need to hit the right balance between the two. But I think it's definitely a good idea to incorporate KG in some regard.
Okay.
Yeah.
Great. Thanks. Thanks, Yugang, for the question. Edward, I know it's late for you. I have hopefully 2 quick questions, depending on how quickly you answer that. Because one question is, you probably heard this also often, right? People saying, oh, this general purpose LM progress so quickly, right? And many people will argue, so you just wait, right? The model eventually
Yeah.
become good enough for your medical specific tasks, right?
Uh-huh.
From your perspective, what's your take on that? Like, what's the real value of building all this medical specific AI models or solution today, instead of just waiting for the general model to become better?
Yeah, I mean, this is an excellent question because I said multiple times today that we should wait.
Right.
But in my head, I think there are 2 concrete cases where you want to fine tune or like build your own model. One is, well, hospitals they don't want to send their electronic records to like commercial LLMs because they're afraid that OpenAI or Google might be taking advantage of their private records. So they want everything to be on premise. So in that regard, hospitals are increasingly more and more investing in building AI clusters and then somehow being able to train with their own medical professors or engineering / medical professors who are able to like write codes in PyTorch and then fine tune an LLM. So they're doing it, but so there's a clear motivation for that, but I'm not sure if it'll ever achieve the same level of performance as like really gigantic LLMs like Gemini 2.5 Pro. Like no matter how much time or how much money or how much data you throw into for example, 70 billion model, because that's usually the best we can do in a single hospital, like 70 billion model. I'm not sure if it'll ever achieve that level of like versatility that Gemini 2.5 has. So I think sooner or later there will come a time where hospitals will have to compromise. Not sure if that's the right term, but they'll sooner or later have to decide, should we keep doing this, like fine tuning 70B models or like 100B models, or do we just give up and then just use commercial model? I think they're experimenting. That's number one. Another one is, if you want to load something onto your like devices, like your Apple Watch or Samsung Watch or iPhone for very specific purposes, I think that's another way to go. For example, if you want to build a ECG LLM that only interprets ECG, I think that's doable with only like 3B or like 7B models, and you can make it small enough so that it'll fit into your iPhone or something. So, but it can only talk about ECG, nothing else. So it's only an ECG interpretation machine. In that case, I think fine-tuning LLM has some value in it.
That makes sense. One thought I had while you were presenting your like that part of the one of your work in the middle, and
Mm-hmm.
I felt the user's capability, how best use of LM to
Mm-hmm.
in a clever way, right? In your case, you actually test the model's capability understanding basic concept before you suggest use this, right? I mean, instead
Yeah,
of
yeah.
just put that in the prompt at some naive rag or that type of approach seems have a huge effect, right, in terms of the per model performance gain. So
Mm-hmm.
I was wondering, maybe even the model itself, it's the same. Maybe the medical, like if you build this medical application in a clever way, it still can extract a much higher performance than some naive user just asks a question, right? Because
Mm-hmm.
often behave much smarter if you ask in a proper way.
Um,
Yeah.
I don't think I got the question though.
Oh, that's just a comment. They're saying that
Oh, okay, I see. I
even
see.
the clever thing you did, I mean, on
Uh-huh.
top of those LM is still valuable because that
Yeah, yeah.
performance. And
Mm-hmm.
even the base model become better, your model will also become better, right? There's no.
Yeah, 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 yeah.
And the other question, the last question, really, I know it's very late for you, is that in the past, right, not very long ago, most of the academic researchers focus on developing new method, right? Okay,
Mm-hmm.
not so much on evaluation, right? Today you talk about evaluation for this AI model. Seems that's a big part of your current research. Do you
Mm-hmm.
recommend this as an area for students or researchers to pursue today over new method development? And also in general, any advice do you have for students in terms of how to select research topics today?
I've never thought about that. That's a very hard question. I personally, uh, I mean, there are a lot of researchers who still train models like NERF or image generation, video generation, or for myself, like synthetic EHR generation. Those are still like those cannot be solved by LLMs. So I think people are still like doing a lot of training and coming up with new methods and stuff. So, but I personally am more drawn to like NLP. I like language, so that is why I'm quite already satisfied with what LLMs can do. Like, I was always drawn to like chatbots and like talking machines. So this like these times of LLM, it's kind of like a present for me. It's a good time to live in. So that is why I'm kind of satisfied with the LLM. I'm just interested in can it do this, can it do that. So eventually, I have some like roadmap that I want to build. Like I want to build like I want to see on LLM that is as similar as human behavior. So in terms like sometimes it just you know ignores me because it's not feeling good, or it's like it's very critical of me because it has a bad day, something like that. Like very very emotional, has own dreams, has own desire, something like that. So I'm interested in that kind of stuff. So that is why I'm mostly doing evaluation. But if it's if LLM is not your forte, if you're not interested in language, I think there are a lot of ways that you can train yourself into training models or coming up with new methods. So I think it depends on what you want to pursue as a researcher.
Yeah,
And I mean, even with LLMs, people do a lot of like cool stuff, like like making inference time faster, or minimizing or downsizing the model size and whatnot. But I'm not interested in that. That's just my preference. I'm
any
just more
general
interested in
advice
the
for students? Because you saw so many papers, right? If in the past, I think we can pretty much pursue any topics, right? If so, okay, this is an
right.
interesting paper. Let's just focus on extending that, right? There's
Hmm.
no really constraint. Today, I felt there's a lot more constraints in terms of what's feasible in the for students or even for academic researchers, right? What do you have some advice on the strategy for picking topic?
Well, what kind of constraints do you mean though?
Like data, compute, and
Oh, yeah.
competitors. Or like, for example, if you say, "Oh, I want to train something beat OpenAI's foundation model," right? That's probably quite hard for
hmm
any individual researchers to do, right? So that type of constraint I'm talking about.
I'm not really sure. I'm not. I don't think I'm experienced enough to give a help. I'd like to hear your opinion because you're more
I
experienced
think
than I
your
am. So.
take on this evaluation is such a great topic because
Oh, for me, so sorry to interrupt, but I think eventually this kind of evaluation needs to be done by the medical professors,
mhm,
um, because they are the authorities. They decide which is useful and which is not, clinically meaningful and clinically not meaningful. So they are the sole deciders. I think I can do this kind of stuff because we're in the intermediate term. Like AI medical professors, they're not as well versed in AI or in engineering, so that is where I come in. But eventually, I think it'll be their responsibility to design these
sure.
very domain specific benchmarks.
I think your framework is much more um, because you understand the algorithm and also the constraint, right? You actually design those things in a way that's much more feasible to conduct
hmm
versus if you just ask a medical doctor to do, they may just maybe do it in a very brute force way that doesn't really, it's not scalable, right?
hmm
For example, you simulate patient. That's actually a great idea, right? And if you say, if maybe the traditional medical person say, oh, we just have to hire
hmm
patient, right? That's cost this much, right? There's like a lot of new ideas, even for evaluation. You have
hmm
explained. I think it's great, and probably you can offer.
Interestingly, there's a Samsung medical professor who has the same idea. I've never talked to her. She just came up with the idea on her own. She's a pediatrician, and she wants to simulate small children because you can't really deploy services directly to the children. So she wants to have a children LLM so that they can play around with the children LLM as a pediatrician. So she already has that idea. She just not well versed in engineering. So she, her pedi- her child LLM is not as sophisticated as my LLM, but still she will get there at some point. So I think the field is like being overlapped very in a very fast pace because these ideas, I don't think my idea is like novel enough. Anybody can think of this, and there are tons of smart people in hospitals. So sooner or later, I'm gonna have to compete with them, which is there's no competition because they're the doctors, they're the sole deciders. So when it comes to like evaluation, I think for students, um, you should pick one that you can run. Like you are the authority. I'm not sure if like PhD students are authority of anything, but still, like for me, I always have to consult to doctors. Like, oh, am I doing this right? Is this kind of question do you feel it useful? Like, does this have to go into the benchmark? Is my benchmark looking good? Like, I always have to ask them and get their okay stamp. But if you want to do if you want to do like an independent researcher, you may not like that. You may not want to be able you may not want to rely on external domain experts to stamp your way every step through. So that's something to think about. I think as a like a starting researcher, like what kind of field do I want to go in? Do I want to go into like law, where lawyers are the sole deciders, like they are the ultimate authority? So you will have to consult with the lawyer every single time. So I think I'm used to it because I've been doing EHR since my
Yeah,
PhD year
I think.
one, so I'm used to it. Yeah.
Look, Edward, it's very late for you, so I think we should probably stop here. And thanks again for the wonderful talk and the question answer discussion. So
Mhm.
maybe hopefully